Here's an introduction to galaxy evolution to accompany chapter 28 of the textbook Astronomy from Open Stax. So we're going to talk about galaxy evolution and pretty briefly, but how do we even know how a galaxy evolves over time? Right? That's something that we should talk about from the get-go. Galaxy evolution is very slow, right? This takes hundreds of millions, billions of years. So you can't just sit and watch a galaxy, right? So if you sit and watch it travel through time at the speed of regular time, that's not going to help you at all. So instead, you can take advantage of the fact that looking further away in space is looking back in time, right? The telescopes are basically time machines. And so the further back you look, the earlier in the universe's history you're observing. And in a sense, it's kind of like archaeology, where the deeper you dig, the earlier stuff you're looking at. I don't want to push the analogy much further than that, but it's similar, at least in spirit. So one challenge is that you need to basically observe lots and lots of galaxies at many different periods in time, and so that you can piece together the likely steps, how things are linked. So it's like putting together the theory of evolution from archaeology, where it's not like we could observe, Homo sapiens emerge. Instead, we're looking at the fossil record and finding lots of different examples, and then eventually realizing like, oh, okay, this is how people evolved over time. It's the same thing with galaxies. You have to find many, many different examples, look way back in space, and then try to infer, okay, this is how, for instance, an elliptical galaxy must have evolved over time. You can also look at clues for the modern day properties of the stars, we'll talk about in a second. And then an important thing too is cross-checking with simulations. So computational astrophysics is an important part of astronomy. So one problem or one challenge when you're looking really far back in time, these galaxies are extremely far away. They're more dim, right? There's not a lot of light reaching us. And so you basically just have the shape and the color of the galaxy, and that's it. You're not going to get any spectra from these things. And one thing you can look at, though, is it's fine with shape and color. You can get a rough idea of what the galaxy type is or what it kind of looks like, and you can count what types of galaxies you have over time. So for instance, when we look really early in the universe, we find we don't really have any giant elliptical galaxies. So one thing we know is that they didn't just form out of nowhere, right? They somehow were not formed at the beginning of the universe. They must have evolved over time. Same thing, you look back, you see spiral galaxies. They're kind of more of like a bulge sort of thing. It almost looks even lenticular. And then as you get to modern day time, you see these, beautiful structures like the Andromeda Galaxy or Whirlpool Galaxy, for instance. And one thing we can do to learn about the stellar evolution or the galactic evolution as well is take advantage of our knowledge of stellar evolution. So we'll do stellar evolution lectures in the future. For now, it's enough to know that stars, live and die. Some stars live longer than others. Stars that are redder tend to be longer lived. And so we can look for red stars versus blue stars. Blue stars are younger, to get an idea of how long a galaxy has been around. If the star is close enough, you can use spectra as well and use radioactive dating. So specifically uranium isotopes you can use to date stars, and then therefore the galaxy that the star is within. And a big problem here is accounting for bias. So the theory of galaxy evolution has changed a lot in the past 30 or so years because of advances in telescopes. So brighter galaxies are much easier to detect, and so when you look back in time, you have a bias that you're going to see the bigger, brighter galaxies. It doesn't mean that there are more of them. It means that they're easier to see. And so you need to take that into account. And more sophisticated techniques have evolved, but then also better telescopes, so we can get a better feel for what the census of galaxies is earlier in the universe. Let's just briefly cover elliptical galaxy formation. So there's two ways you can kind of think of them being formed. You can think of a top-down method, meaning you have basically just a thing kind of form at once in a big collapse of a cloud. Or the alternative option is to have bottom up, right? So you have little galaxies or little proto-galaxies combining, and they combine over time to make your elliptical galaxies. So either one of these are sort of plausible scenarios. So looking at the top down, why do we think that that's one way ellipticals can form? So when we look at the early universe, what's the observation that we make? We see these things called quasars. We believe that they are, because they're extremely bright and because of the timescale variation of the light change, they more or less have to be supermassive black holes. And they're supermassive black holes feeding on galactic gas. They make these extremely bright jets that they outshine the entire rest of the galaxy. So they're very bright, so we can see them back into the mists of time, right, into the very early universe. So the fact that we see these means that there must have been some large galaxies forming early in the universe, right? So shortly after, a few 100,000 or million years after the Big Bang, when the universe is cooling off and gas clouds begin to collapse, you must have had some rather large gas clouds coalescing to ultimately form an elliptical galaxy, right? And the sub-gas clouds inside that will collapse to form stars. Okay. Now, if you remember the Milky Way formation lecture, you'll remember that a collapsing gas cloud ultimately forms a disk. So you might say, well, why do you not have a disk for the ellipticals? The idea in the top-down scenario is that it's because you have very little net angular momentum. So you'll remember from the Milky Way formation lecture, if you follow the particles in your gas cloud, the idea is that some are moving left, right, up, down. And if you sum all these together, you very likely have, kind of an average, let's say, rightward motion in this picture. And really it would be a rotational one. And that those will eventually collide and average out to form a disk. Well, it can be the case that you happen to nearly cancel all these motions. So they average out to roughly zero. Well, then you wouldn't necessarily form a disk. So in this scenario, that's completely plausible, and so there's some observational evidence we have top-down formation of ellipticals. Now, alternatively, we note that if you look back in time, you don't see giant elliptical galaxies earlier than about 6 billion years after the Big Bang. They just are not there. And because they're very bright and big, you would see them if they were there. So that means they weren't formed then. And yet now, when we look more recently in time, we do see very large elliptical galaxies, things with trillions of stars. And so what that means is that these large elliptical galaxies must have been formed by some kind of bottom-up mergers. So we see galaxy mergers occurring in space, and the idea is that merging of galaxies can create something like an elliptical. And why you wouldn't have a disk in this case is that, remember that the key to disk formation is you have a gas cloud collapse and you have gas particles colliding. There's a high density of gas. It's not that you have individual stars colliding. So by later in the universe, your galaxies tend to not have a whole ton of gas in them, right? Spirals have a lot, but it's not that much. And so you just simply don't have enough gas particle collisions to create this sort of flattening, to average the angular momentum into a flattened disk. And so instead you can have stars orbiting in lots of different directions around the center of the object. And so it just looks like a spherical-ish or spheroidal blob as opposed to something that's flattened into a disk. And just want to make it clear here, both of these appear to be true, right? So there's observational evidence for both scenarios, and there's no reason you can't have both. So smaller elliptical galaxies very likely formed in a top-down style, whereas the larger ones had to have formed in a bottom-up style. So with spiral galaxies, we have a little bit different picture. It's not that different. It's mostly considered to be a bottom-up formation, though really it's kind of like a little bit of top-down and then mostly bottom-up. So the observation that we have is that spiral galaxies, if you look at the bulge, you see mostly older stars. if you look at the disk, you see a lot of younger stars. And so the bulge must have formed a long time ago, and the disk can have formed a lot later. Okay, and so then we have another piece of observational evidence that if you look at, for instance, at the Milky Way, you see chemically distinct stars and streams going through the Milky Way. And what I mean by chemically distinct, it's stars that formed kind of together at the same time in that little stream, but not at the same time as the surrounding stars, right? So it's like a fingerprint kind of streaking through the sky, if you will. It's a rough analogy. And so that means that spiral galaxies must grow by mergers with smaller galaxies. It has to be smaller because if you have two really big galaxies collide, you'll completely blow up the structure and you'd get an elliptical. But if you sort of accrete or consume, if you will, smaller galaxies, and it's not going to really disrupt the structure, you're just going to kind of absorb those stars. And so the idea then is you have a two-phase process. So you have something that's kind of like a top-down for your spiral galaxy, where you have a gas cloud collapse into a blob. The gas collisions allow some of that blob to form a disk. And then, as time goes on, in the nearby neighborhood, there are other little galaxies and little globular clusters, and these can get absorbed into your galaxy. They can help grow the bulge, and then also that merger will help seed star formation in the disk. So what about galaxy cluster formation? So the concept, to first order is very similar to galaxy formation. So you have early in the universe, you have local perturbations in the density, and some of the regions that are a little bit more dense than others are going to collapse. And you're going to have a pretty interesting structure in the local density. And so if you look at the beginning picture here, this is a simulation. You're supposed to see slight overdensities where it's a little bit brighter, and those regions are going to collapse more than others. And as time moves on, you're going to create this sort of filament structure. It's something that we often refer to as the cosmic web. So what this picture is showing is basically galaxy clusters. Each little tiny point is a galaxy. The little blobs that you see, these would actually be galaxy clusters, and these streak together to form a kind of web structure around us. There's nothing special about where we are in this web. Really, it's kind of essentially infinite in extent, at least as far as we can see in the visible universe, and we have no reason to believe that we're at a particularly special location. And this isn't just from simulations. We've actually observed this cosmic web, though the observations, the strong observational data, is actually relatively recent. Not only in your lifetime, but even in your adolescence, young adulthood. So, for instance, this is from the Sloan Digital Sky Survey, and each point here is a galaxy, and there are open spots because of observational limits. But as you're looking outward here, you're getting further away. So further from the center is further away with the distance given in redshift. And you see that filament-like structure just like we saw in the simulations. And there's nothing particularly special about this region that has a lot more material than the others. It just means that early in the universe, this region of space happened to have a little bit higher density than the other regions. And then on the right is a detailed view of part of the cosmic web, but looking at some gas, and you can use spectra to get gas velocities. And here you can even construct a 3D picture of this gas filament. And again, like the galaxies here, these are just tiny little blobs, and the symbols here, these are indicating different types of galaxies. So you have a filament structure. And just to wrap things up, if we zoomed in on those filaments a little bit and we looked at galaxy clusters and we try to figure out how those are forming, it's the same picture that we've been looking at for galaxies. It's true for stars as well, is you basically have local density differences, and then gravity causes those to preferentially collapse, and then you just put together time. You just wait. And that's, the simplest way to explain all of this is density differences, gravity, and time. And that is it for this introduction to galaxy evolution for Astronomy 1000.